Well, I'll try to record my lecture here today. Okay, so before we continue on double integral, let me ask you a question here, just to see you have an understanding of the constraint type of problem here. So it's a multiple choice question. Okay. Consider we have a cost function z equal to f of xy and a constraint g of xy equal to c. And here are the four choices. Which one of the following statements is false? Okay, let's read it together. A, at the critical location, directional derivative df over ds is 0. B, at the critical location, del f is parallel to del g. At the critical location, del f is perpendicular to del g. At the critical location, level curves for function f is tangent to constraint g of xy equal to c. There's four choices. So which one of the statement is false? Yeah, let's see here. Yes, right? The correct answer is C. And the correct answer is C. It doesn't mean that C is correct, okay? I mean, yeah. So basically, at the critical location, del f will be parallel to del g. That's how we derive our Lagrange multiplier, right? So at a certain critical location, del g, u hat, and then del f, they're probably parallel to each other. And if there is a level curve, of course there is a level curve, then at a critical location, the level curves from the function f and the constraint g, they will be tangent to each other. Right? So I demonstrate that using the maple animation in the previous lecture. Okay, so that's basically the constraint problem. We started the double integral concept. Okay. So this is what we just started. Basically, this is the problem we formulated at the end of the previous lecture. So the problem here is essentially given you a surface z equal to f of xy and a region R, okay, in the xy plane. Then what will be the volume underneath this surface and above the region R? Okay, so it's like you're creating a bucket here, okay, but with the top is the surface, bottom is the region R. So how would we be able to calculate the volume of that? So let's see how we can formulate this problem, how we can calculate this problem here. So this is how we can do here. So we can, within the region R, right? So within the region R, let's pick a point. Let's pick a point within the region R. And this point picked here, let's call it xk, yk. So this is the location of the point. And then we're going to create a very, very small patch around this region, around this point, xk, yk. So by small patch basically means, you create a delta xk and then delta yk, okay, around this point. And then we can create a rectangular, not really a rectangular box, but we can extend this patch, okay, all the way up to the surface. Okay, so all the way up to the surface. So basically extrude it up to the surface. Right? So you're creating essentially more or less like a rectangular box. But of course the top of the box is the surface. Okay, so that's not, technically it's not a flat surface, right? But if you create it small enough, so you can still think of it as a rectangular box. So now you create that box here. So the question basically is, what will be the height of the box, right? Height of the box, consider if this is a really very small patch, it's a rectangular box. then the height of the box can be represented using f of x k, y of k. So that's the point, right, within this patch. Then you extend that point to the surface, you get this much height. So we can use that as the height of that little rectangular box. Now, once we get this clear, then we can see, okay, so the volume, okay, of the rectangular box is approximately the base area multiplied by the height. So height is f of x k, y k. Base area is delta x k times delta y k. Okay, so this portion here is the base area. So you get the volume of this very, very small rectangular box. Of course, my drawing here is very much exaggerated. Okay. So now you can imagine if I can create n number of these rectangular boxes within this region R. Right? So then you get, so the volume under z equal to f of x, y above region R, it can be approximated using summation. Right? So you're summing the n number of the boxes, rectangular boxes. Each one of them has a volume of f of x k, y k times delta a k. So if any number, you add them up, you get the approximated volume, right, underneath the surface and above the region R. Okay. As usual, we let the n goes to infinite. So we create as many as possible. Then the delta xk becomes dxk, or just call it dx. And then delta yk will become dy. So all the delta, and then summation sign will become integral sign. Then the volume we're calculating at it here, so this formula here, right, can be, right, let's just steal the same description at here, becomes, right, integral here. Right. Not only one integral, now we have two integrals here, so then I'll explain. Basically, the summation at here becomes integral. And you're integrating this function f of x, y, okay, and then this area delta A becomes dA. So dA basically equal to dx times dy. And so that question, right, laid out at the beginning, okay, which is the volume underneath the surface above the region R, can be calculated using this formula. Yes?
It's not a phone call. Is this lecture going to be recorded and put on campus? Because it's not live right now.
That's right. So I'm recording it. Yeah. Good. Am I? Yes. The question here is, you might, so how come you have two integral sign here? So this is called a double integral. The reason we have two integrals is because now we got two variables to worry about, the x and y, right? So this is called a double integral. And formally, if I had to describe what we just derived here, right, is that you can see this is what we're doing here is integrate this function, right, integrate this function here over the region R. And the f of x, y is defined over R. So if you don't necessarily have always associated one formula with one physical meaning. Right? So the way right now this is derived here is based on the formulation of volume problem. But later on, you can see this double integral can certainly be used for many other different physical characteristics or physical meaning. Not necessarily it's always just the volume here. Okay? So irrespective of whatever the physical meaning is, when you see this double integral, so what you're doing is essentially next what we'll see is we integrate this function over the region R. So integrate this over the region R. Okay. One of the assumptions we're making is the function has to be defined over the region R, because what that means is you're integrating this function over region R. The region R has an infinite number of points, x and y, right, within this region R. So if you pick a point within the region R, then you plug it into the function f, then the function f has to be able to spit out a value for you. That's what basically means this function is defined over the region R. Okay? So sometimes the function is not defined, then you actually cannot integrate this function over the region R. So we had to assume, we're going to assume that this function is defined over the region R. Okay, so the question here is basically is how to properly compute this double integral. So we'll look at quite a few different approaches, okay? But there's one single approach that I'll point out as is the meaning is to scan through the region R. It's a concept how to scan through the region R here. All right, so I usually use this as an example to illustrate how would you do it. Okay, using this loaf of bread as an example to start with. So you have a loaf of bread here, okay, and it's cut it into pieces. Right. Now, what we could do is, okay, let's make an analogy at here. So let's say this is x, y, z. Okay. So you put this loaf of bread into the xy plane, xyz coordinate system. Okay. Then assuming the bottom of this loaf of bread here, right, is in the xy plane. So assuming the bottom here is your region R. And then the top so the top is your surface z equal to f of x, y. Right. Okay, so now you go to the store, you look at the loaf of bread, and you might wonder, so what is the total volume of the loaf of bread? Right? So we need to calculate. You want a loaf of bread as big as possible, right? So that's most economical. So let's take a look at how we can calculate using this one here. So since it's already sliced, okay, so we might actually be able to find the volume by finding all the volume of the slices, and then you add them up, then you get a total volume of the loaf of bread. Okay? Yeah. So here's a detailed procedure at here. Okay? So the steps here, so I'm going to list the step, but what I'm going to list here is that there's a concept here, okay, that I will emphasize also many times in the future. The concept is to scan through the region R. Scan through region R, okay, with no redundancy. Here's the approach, general approach we're going to use. How you can scan it through, and at the same time, we're not scanning it twice, we're not scanning it with redundancy. Okay? So scanning it with no redundancy. That's what we call integrate over this region R. Right? So this is basically how, what do we mean by integrating certain function over that region R? Okay. So let's use this drawing as example, a little drawing from lecture notes and here. Okay. So now step one. Just remember this is the region R over here. Step one, you scan in the direction of y-axis, the order can be reversed as we're going to see. Okay? So scanning the y-axis basically means like this. Okay? So this is what we're doing here. So this is y-axis, right? This is y-axis. So you create an arrow line in the y-axis. So you're cutting through this region R. Cutting through the region R along the direction of y-axis, parallelly. So it's like the bottom, basically the bottom line here, right? You scan it through. So that scan, which is the first step, so technically, when you're scanning through, or when you're cutting through the region R, you're creating, right, this red, or this green color, okay, segment line in the region R, okay? At the same time, right, when you're scanning through, you're creating this line in here. So technically, what are you doing? You're creating a cross section, okay? A cross section along this parallel to this z-y plane. Okay? So that's basically the first step of scan in the direction of y-axis. Okay? Then by doing this, so let's single out that cross section there. Okay. So if you look into the direction, into the ZY plane there, so what you see here is you see a cross section like this. Okay. That's a result of the first step of scanning. Okay. Right. So if I had to label this correctly. Okay, so you can see the first time this scanning here bump into this part and then exit at this part here. Right. So whatever the location you're scanning, arbitrary scanning, so you get a y mean value over here and then you get a y max value over here. Right, so that this part here, okay, the green, so let's use the green, is the green over there. Right. So this y mean corresponding to the value over there, the y max corresponding to the value over there. Okay. And this top here is determined by the top surface of the lobe of the red. And so that's basically give you the cross section in here. So what this part of the curve, right? This part of the curve of the cross section here, this is y, this is z, comes from the top surface, which is z equal to f of xy. So this part of the curve, technically, right, is part of the f of xy. So you can label that as f of xy, right? Okay. So once you get this, then you can literally see, okay, so then what is, if I create a very small volume of a slice of bread around this location here, okay, then what is the volume then, right? So you can start trying to calculate the volume here, but first calculate the area, okay, of the cross section, and then multiply by a very small change, okay, over this area here, right? So let's calculate the volume of the slice. Volume of the slice here. So volume of the slice equal to the area of the slice the area of the slice, a second here. Right, and then multiplied by thickness. Okay, yeah. All right, so what do we get for this? First of all, let's deal with the area of the slice. Area of the slice is basically the cross-section area. Right, so what does that give us? So let's calculate the area of the slice here, and you look at the current, what we're dealing with we have a y mean, right? You basically integrate, okay, to get the area underneath the curve. Right? You integrate under the curve, which is f of xy, and then dy. Right? So that's the area of the slice. Now you might wonder, so what happened to the fxy here? So you're integrating this function, integrating with a dummy variable y, right? Because you're integrating along the y-axis to get the total area underneath this curve. Right? Now because the reason is, remember the first step, you're scanning the y-axis. So basically you picked anywhere, you scan it. The anywhere is the x location. So while you're going along the y-axis direction, the x value is being treated as if it's a constant. Right? So that's basically, even though you do have both of the x, y here, but you're treating x as if it's constant, because you're not changing x. You're scanning in the y-axis direction. And then times the thickness. So thickness is in this direction, right? So let's call this is dx, like that. So that times the dx, okay? That will give you the volume of that one infinitesimal small slice. Okay? Okay. So that's step one, right? Scanning in the y direction. So now let's see the step number 2. Okay. Step 2. Okay. Once you've done the scan, then the step 2 is to scan in x-axis direction. Okay. Scan in this direction. So scan in this direction basically means you are going along the x-axis direction. So it's like you're moving, you're scanning, right? You have a cross sections right here, which is that piece of a slice of a bread. So you're like creating a 3D object. Okay, you're from one end all the way scanned to the other end. At the end of the scan, you have this whole piece of the whole loaf of bread created. Now, imagine you're like using a 3D printer. So 3D printer basically will first print one very thin slice like this, right? And then it will keep printing on top of that, and to give you the whole geometry of the object. Right? So that's the second step of scan in the x-axis direction. And what you're doing essentially, mathematically, the scan meaning is you are adding up, right, all of the volume, along the x-axis direction. Okay? So you have the dx over here. Then the second step of scan is you try to create the total volume of the bread. Okay? So what I'm doing is, right, technically, it's like if you use a finite concept, you have a volume of one slice, and then you times the number of slice, right? Whatever number slice. But if the number of slice is infinite, then you get an integral. You're integrating from one end to the other end. And what are you integrating? You're integrating this quantity at here. So you get y mean, y max, f of xy, dy, and dx. And so finally, that gives you the total volume of the bread as an accurate number. So the order, as you can see here, at the end of the day, you have two integrals. Okay? The first integral is about the variable y, and that's what we call the scanning in the y direction through this region R. And the second integral is about the x variable, and that's about the scanning in the x-axis direction. Okay? So this way, you completely finish the scanning of the region R. At the same time, you're not causing any redundancy due to this scan. So that gave you this breakdown integrals, right, for the original formula, which is this one. Okay? And the limits for the two integrals. y min, y max, x min, x max, will be determined by the region R, as we're going to see. But the final result, like this, if your region R is a given region with all the values properly defined, then the final value should be a constant value. So the final value shouldn't be a function of x or y or a mix of x and y. It should be a number. Right? That's basically a result of the double integral. Okay? And of course, now, a natural reaction is, so if you scan first in the y-axis and then x-axis, so can you switch the order? Would you be able to scan in the x-axis direction first and then followed by the y-axis direction? The answer is yes. Right? So you can certainly change the order of scanning or integration. So change the order. It is definitely doable. So all you do is, right, so you're still integrating this function. But the first step, you're integrating in the x direction. And then the second step is in the y direction. Okay. But one thing that you have to be careful, as we're going to see through examples, is that, so although my integral limits, okay, notation-wise, okay, it looks like the same, y min, y max, y min, y max, right? Yeah. But in reality, when you do this, when you switch the order, the y min, y max out here, okay, is not going to be the same as the y min, y max over here. Okay? But for some cases, yes. But in general, they're not necessarily it's going to be the same. Okay. Okay. So both ways are good. As a matter of fact, some order, sometimes your order of integration will actually make your calculation easier. So sometimes order really matters. So let's take a look at a simple example here. Let's just suppose I have a surface z equal to f of x, y equal to 4 minus x minus y. And then we have a region R given, which is x between A and B, and y is between C and D. So here's your region R, and here is your surface. So let's say we give a number. So A equal to 0, B equal to 2, C equal to 0, D equal to 1. So for example. Okay, so if I had to sketch this, sometimes from nowadays you need to practice a little bit of sketch illustration. Being able to sketch will help you understand the question. It doesn't have to be very accurate sketch, okay, as long as it makes sense. That should be okay. So first, you always try to sketch the region R first. So if you look at the current region R, x is between 0 and 2. So 0 and 2 here. Y is between 0 and 1. So 0 and 1 is right here. So basically, the region R, okay, is a small rectangle box. And then the function z, okay, is 4 minus x minus y. Okay. So that function technically is x plus y plus z equal to 4, right? If you put them together here. So I think by this time, when you look at this one here, you should be able to know, okay, that must be a plane, right? It must be a plane. So now the question is, how would you draw the plane properly? That really doesn't matter, but you will gain some experience. How would you draw the plane properly? Okay? So that plane has intersection. You can more or less illustrate the plane by finding the intersection between the plane and each one of the side of the plane, xy plane, xz plane, and zy plane. Okay? Yeah, you can more or less do that. But in this case, the plane, okay, will more or less look like this. But remember, you're only looking for integration is within the region R here. So you do have a plane on top of the region R, but the plane is infinitely big. So for any of the area of the plane that's actually beyond the region R, then that's really not part of this integration problem, right? So you're only looking at this, the part of the plane that's right on top of this region R. Okay. So the plane probably look like this, right? Plane. So, but you are really looking at, right, is you extend it up. Okay. What you're really looking at is maybe something like this, right? On top, that's the part of the plane on top of this region R. All good? Yeah. So that's sort of a very rough illustration. Then when we do the integrals, right? So step 1, order. Okay. So order basically means, what are you going to do? Are you going to do dx, dy, or are you going to do the dy, dx? So which integration you want to integrate first? Usually it doesn't really matter, okay, but sometimes it does matter. Okay, so let's try the dy first and dx next. Okay, so I'm going to try dy and then dx. Okay, that will be my scanning order. Okay, so then I can actually sort of lay out the double integral right here. So I'm integrating this function. First integral is about the dy. Then what am I going to do? Right? According to the steps, you're going to create a scanning, okay, in the y-axis direction. So find anywhere to scan through this region R. So in this case, the region R is a rectangle box. So as you can clearly see, if you draw the line here, you get a y mean 0, y max is 1, right? Now if you draw it somewhere else, you still get a 0 to 1. Okay? So the y mean, y max, it doesn't matter where you draw, okay? It's always 0 to 1. It's a constant, which is great. So that gives you the limits of 0 to 1 for y mean and y max. And then you can integrate, the next step is to scan in the x-axis direction, to scan through the whole region R. So what you're doing basically, you're going to move across, right, the axis direction at the same time across the whole region R to scan it. Okay. As you can clearly see, right, your limit for the x mean is this, starting from here, which is 0, and end up at here, which is 2. So your x mean is 0, and x max is 2, so 0 to 2. So once you find the limits of the integrals, the rest of the work should be relatively easy. So let's plug in the function f. That's 4 minus x minus y, dy here, and dx. Okay, so now you calculate the integrals one by one. So work in and out. So the inner integrals, when you integrate with respect to y, you're going to treat the x as if it's constant. Okay? So don't touch the x, just think of it as a constant, very much like the partial derivative, right? Yeah. So the inner integral should give you 4y minus xy minus 1/2 y squared, and let y go from 0 to 1, and then dx. So calculate the result of this inner integral. You get 4 minus x minus 1/2 dx. And then the last one is just regular integration. There's nothing tricky here. And you're going to get a 5. Okay. So 5 out here, if you have to relate to the volume concept, basically what it means is the volume above this region R and below that surface, the plane, give you a total volume of 5. Which kind of makes sense. You got a positive volume like that. So that's a simple region, right? As you can see, the reason that the region is simple is because right now the region is a rectangle box. Yes. Do I have to plug in the value for which one? Or you plug in values at the end? You could, I guess you could, right? But you will suspect to more maybe mistakes if you start plugging values at the end. So I don't see any reason why you wouldn't plug in value at this stage. So then you get rid of all the y, and then you only have the x to deal with, right? So, I mean, you could. So you could keep the, you can certainly keep the y variable as a variable, right? But I wouldn't recommend that. Okay. Is that good? Okay. So I want you to try yourself, what would be the volume, okay, if I change the order? Or what would be the limit if you change the order? So basically, instead of the dy dx, you do dx dy as this new order of integration, of scanning. So for this question, you can try it. I mean, should be pretty straightforward. You just have to change, because it's rectangle box, so the limit's just flipped. Okay? 0 to 0 to 1, like that. So you should get exactly the same answer though. So 5. Okay? So that's a simple one, right? The simple one means it's a rectangle box. As you can clearly see, all the limits, integral limits here, they're all constants. So now let's take a look at a relatively general case. Without specifying what the function we're dealing with, but let's more focus on the region R. So region R is bounded by x squared plus y squared equal to 1 and x plus y equal to 1. This is key information. I want you to be able to interpret this information even if the question does not provide you with a graph of the region R. So then you can still graph it out. Okay. So to graph the region R, all you need to do is, okay, you can graph this region R in an XY planar case. You don't have to graph it in a 3D. Right? First, graph this x squared plus y squared equal to 1. Okay, that's a circle. Okay. And then you graph x plus y equal to 1, which is a straight line. So I do notice sometimes, especially when I teach the other course, some students not quite familiar with how the straight line is constructed or how to properly draw a straight line. Right? So if you're having trouble with that, you need to brush up on that part of the knowledge. Okay? So they definitely, right, the line here, x plus y equal to 1 will pass this point here. It says the region R bounded by this. So basically, this little area, right, is your region R. So now you can, once you get this, you could get rid of the rest of the region, and you just have to draw a region R out. But make sure you label this properly. So this is x plus y equal to 1. This is x squared plus y squared equal to 1. And also label the critical locations, right? I mean, this is 1 here, this is 1 here. But you need some of the information to properly calculate the limits, okay, for your double integrals. Okay? All right. So once you find this region R, now I did not sketch this surface, but I think in your head, and you have to be very firmly know, what we're dealing with here, right? So what we're dealing here is technically, so basically your region R is in the xy plane, and then you have some sort of surface on the top, right? And then you're trying to get the integrals of this function over this given region R. Okay. The reason I'm not scanning like this is, is because nowadays, as you can clearly see, the focus is to find the limits. And the limits can be found by properly scanning through this region R. Right? So I don't have to draw 3D. The integrand here is exactly that function, z equal to f of xy. Okay? Yeah. So here's the proper procedures. Right? Here's the proper procedures here. First, decide on the order. Okay, decide on the order. Order of integration. So let's say I'm choosing dy dx. Okay, that will be my order. So meaning I'm going to scan in the y-axis direction and then scan in the x-axis direction. Okay. So let's formally reiterate the steps here, right? So what do? You can draw, let's just draw an arrow lines across R in the positive y-axis direction. Okay, so here's what's going to happen here. Let me use so I'm going to draw in the y-axis direction like that. Right? So that's what we're going to do. We draw it across the region R. Okay, that's the step of scanning in the y-axis direction. And then you go and you look for, okay, the so-called first contact point and the second contact point. Okay, so that's basically the steps set here. So first contact point give you the y mean. Okay, give you the y mean. So you look at the first contact point in this question here. What you're scanning here, the first step is a general scan. You could draw it here, you could draw it here, right? It doesn't matter where you draw it. Okay. But it really doesn't matter where you draw it. The first contact always falls onto this straight line. And we said the first one gives me the y mean. So your y mean should be determined by the expression for the straight line. As you can clearly see, you draw it here, you got a y mean of maybe 0.5. You draw it here, maybe you got a 0.6, right? But in general, we're looking for a general expression. So your y mean should be from the expression of the straight line. The y mean should be what? Y minus x. Because that's the straight line equation. Y minus x give you the y mean general expression. And then second contact point will give you the y max. Second contact point, sometimes we call this is exit point. So basically, first contact can be called entry point. Okay, that's where you start to get in contact with the region R. The second one is where you exit the region R. So as you can clearly see, the second contact point always falls on that circle. So the expression for y max should come out of this circle equation here. So circle equation, right, because we're talking about this is a circle in the first quadrant, so you get square root, okay, y minus x squared. That's your y max expression. Okay. So the first step of scan technically presents you with one segment of a green line over there. Okay. And after this, then you do the second step of the scan. Okay. So technically in the positive x-axis direction. And this step is to find x limits. So for this step, what you do is, right, remember the first arrow line you created. So this step here, you start from one end of this region R, then you move all the way in the positive axis direction, okay, to go across the region R. As you're going moving, then you find, okay, here's one end of the region R, here's another end of this region R. Okay. The two ends of the region R, which of course determined by the geometry of the region R, will give you this so-called either x mean or x max. Because when you're in your head, you can think that a 3D printer is working. So it's basically scanning through and printing, to create that 3D object. Okay. So this step right here, right, is to sweep the arrow line across region R. You will notice there are two edges. The two edges will give you x mean and x max. So obviously in this case, your x mean is 0 and x max is 1. Right? That's how the two edges determine based on the region R. So then overall, once you get done this, then you're done with finding the limits for the integral, and you just have to set it up. So you're integrating certain function at here with an order of dy dx first, dy first, dx next. And for this particular region R, we have just found that y mean is y minus x, y max is y minus x squared, and x mean is 0, and x max is 1. So now, if you have the function given, you'll be able to calculate from the inner integral first and then do the outer one, you get a number here. So that's the idea of a double integral, the scanning. So I want you to practice yourself is, how about if I change the order? What would be the limit if I change the order? So dx first, and then dy next. Same region, okay? Same region. So this time, you're going to create in the x-axis, so you scan in x-axis direction. This is your first contact. This is your second contact. Okay. And then you move around, scan in the y-axis direction cross to find the y limits. Okay. So we'll look at that. Maybe I'll just write it down here. Okay, so when you scan from here, you get y minus y to square root y minus y squared, and this is 0 to 1, right, to get you the limits. Okay, so we'll look at an example in the next lecture, okay, and then we'll look at more about other approaches of calculating a double integral. Any questions? So feel free to come over here.